graph neural networks as well as CNNs and so on, right? So if we look at these three different objects, right? So we have graphs, we have grids, and we have meshes. So we talked maybe briefly about all of them and mostly about graphs, but you can see that they're roughly the same, right? So the graph is the most general. A mesh is a graph with some extra structure, right? So in addition to nodes and edges, you also have triangles. So it's called the simplicial complex, technically. And a grid is a special case of a graph, right? So it's a graph that is connected in a particular way, right? So when I aggregate information on each of these objects, so when I'm on a grid and I have my node here, right? So this is my node. I have a canonical order of the neighbors, right? So I can always designate my top neighbor, my bottom neighbor, and so on and so forth, right? So there is no ambiguity in the way that I aggregate information from the neighbors, right? So this order is fixed. When I'm on a mesh, I can decide which of my neighbors is first, but then the rest of the neighbors comes in, for example, clockwise orientation, right? So I can define everything up to rotation, right? So if you remember, I mentioned the gauge transformation, so that's exactly it, right? So it's the local choice of the system of coordinates. So that's basically who is my first neighbor, right? So how I rotate my local system of coordinates, right? So everything is defined up to a rotation, right, or a cyclic group. And on a general graph, I can permute my neighbors in any way I want, right? So basically, it's defined up to a general permutation. So in a sense, graphs somehow have the least amount of structure out of all these objects. Now, another thing that you notice is that I can think of grids and meshes as discretizations of something continuous, right? So a grid is a discretization of the plane, for example, or a mesh is a discretization of a surface or a manifold. We don't have this immediate analogy for graphs, right? So what are the graphs? So they already come discrete, right? So we want this kind of continuous model for graph neural networks. And this will be this physical metaphor, which, well, I hope it will be, you will find it interesting. You can also relate it to the previous discussion, right, about spectral analysis and differential equations. So I want you to think of GNNs, right, and learning on graphs as a dynamic system, right? So imagine that your graph, the nodes are particles. They live in some d-dimensional feature space, right? So remember, every node has d-dimensional features. So in this feature space, every node has some coordinates. And these coordinates evolve in time, right? So they follow some trajectories that I denote here by these red curves. And they're governed by some system of differential equations, okay? So here the time t is the position on this trajectory, okay? Now, what are the layers? So I can just sample my time with, for example, fixed step, right? So let's call it tau. And this will be discretization of time, right? So these will be the layers. Now, what is a graph? So the graph defines how the particles interact. So they don't move independently. They interact with each other. How do they interact? Along the edges of the graph, right? So the graph has the role of a coupling function, right? Between these particles. We'll see also that we can consider it as some sort of discretization of a continuous spatial object in some cases. Okay? So out of all the possible differential equations, because what is written here, I can put more or less anything I want, right? So what would be a reasonable thing to consider? A diffusion equation, right? So when you think of propagation of something in some medium, diffusion is probably the first thing that comes to mind. I already mentioned it. So it was the first physical phenomenon studied in a rigorous mathematical way by none else than Newton himself. And I already mentioned the Newton law of cooling. So it tells that the temperature a hot body loses in a given time is proportional to the temperature difference between the object and the environment. And basically, that was the early formulation of the heat equation. We can basically combine it with some conservation law and say that the heat flux, right, which is proportional to the gradient of the temperature, and the conservation condition, right, that heat is not created and it doesn't disappear, give us the heat equation, right? So the divergence of the gradient of the temperature is proportional to to the temporal derivative, right? So that's how the temperature changes in time. And we can, of course, consider the different versions of this equation. We can consider homogeneous and isotropic case where the heat conductivity is the same everywhere, right? So we can take this constant out, and the divergence of the gradient is just the Laplacian, right? So that's the simplest version of the heat equation. We can consider also non-homogeneous and isotropic, position-dependent diffusivity, right? So divergence of some scalar function multiplying the gradient. And the most general case is what is called the isotropic diffusion equation, where this matrix is also not only position but also direction dependent. So it's basically a matrix valued function that multiplies our gradient. Okay, so what is another thing that you need to know is that you can think of the heat equation as the gradient flow of the Dirichlet energy, right? So the solution of the equation will be minimizing this Dirichlet energy that we have already seen before. And on a grid, in the Euclidean case, you can actually write it in a closed form. So you can write it as convolution with a Gaussian filter of increasing variance. So as time goes by, I'm basically convolving with a bigger and bigger filter. And as a result, I get something like this, right? So in the limit, everything will become just the average pixel intensity, okay? So this is the homogeneous equation. I can also consider a non-homogeneous equation. So this was very common in the image processing literature. So I can decide that when I want to filter my image, I can decide that I don't mix pixels of different color. So basically, I have here a way of slowing down or making the diffusion faster based on the size of the discontinuity, right? The norm of the gradient. So it looks like this. And this is also another functional that we can define. So this is called the total variation. So you can think of it as a gradient flow of a total variation, which looks like Dirichlet energy, but without the square. And this is what it does to the image. So it averages in similar regions, but it doesn't average across the discontinuities. And there were tons of literature written in the computer vision and image processing community in the 90s and early 2000s. It is very mathematically elegant and appealing idea, right? So I define a functional and I minimize it, and this somehow tells me how my image should look like, right? So I can basically define my processing technique as a differential equation that basically is a flow that evolves, that minimizes these functional. And you can also relate it to graphs, right? So there was this beautiful review paper by Payne and Milanfar, who was considering these different filters from the perspective of graph signal processing. Now, how does it look on a graph, right? So we talked about diffusion equations on images. So on a graph, it looks exactly like this, right? So this is how a heat diffusion equation looks on a graph. So we have the temporal derivative on the left-hand side and the Laplacian on the right-hand side. And we know how the graph Laplacian looks like, right? So this is the divergence of the gradient, and we can write these operators on the graph explicitly, right? So what is the gradient? It's just the difference between the features at two endpoints of an edge, right? So just xi minus xj, right? Or xj minus xi, right? So it basically takes a signal that lives on the nodes of the graph and makes it into a signal that lives on the edges of the graph. And what is the divergence? It's the opposite. So I take all the edges that share a node, and I sum up all the values on the edges that emanate from this node, and this is the divergence. So I get again a node-valued signal. And if I just rewrite it in a slightly different way, again I get the same thing that I've seen before, right? So it's the difference between myself and my neighbors, right? So this is the average temperature of the environment. This is the temperature of the object itself, and this is the rate of temperature change. So it's a graph local version of the Newton's law of cooling, right? So this is how you propagate information on a graph. And again, on a graph as well, it is a prototypical gradient flow, so it minimizes the Dirichlet energy, right? And the Dirichlet energy on a graph looks like this. So basically, I can write it as a quadratic form with respect to the Laplacian, and what it measures is the smoothness of the node features, so how different I am from my neighbors. If I'm not different, the Dirichlet energy is low, okay? So it increases along the flow, and if I take it in the limit to t goes to infinity, it will result in what is called oversmoothing. So if I think again of this dynamic system, all the features will collapse into a single point, right? So somehow it's considered as a bad thing, right? Because, well, if all the information that is contained in these nodes is somehow lost. But imagine that I want to do to do node classification on the graph, right? So I know some labels of some nodes, and I don't know some other labels of some other nodes, right? So what do? I can consider it as a diffusion equation with boundary conditions. So I fix the values, right, the labels in the nodes that I know that are labeled. I fix them as a boundary condition and just propagate this label on the graph, right? So I solve the diffusion equation with a boundary condition, right? So it will look like this. So I can basically simulate a few iterations of this process, right? And this is how it looks like. So it works extremely well. You don't need any learning, right? So I just propagate the existing labels. It even has a closed form solution. So I can write how this matrix looks like, right? So and we have this, the labeled part is fixed. The unlabeled part is the one that I'm interested in, right? And basically I can write this limit like this with matrix inversion. It works well only under the assumption of homophily, right? So this is the assumption that my neighbors have similar labels to myself. If this assumption is violated, then this label propagation doesn't work, right? And therefore we will need to do some learning, and that's why we need graph neural networks. Any questions? Okay, but basically that was the analogy, right? So that was without any learning. So again, if we think of our learning on a graph as a dynamic system, so the standard approach, the traditional GNNs would say that start with some system of equations, discretize them, right, and parameterize each step, right, or each iteration of this equation. So each step in time, in discretized time, corresponds to a layer, right? So we parameterize every layer with learnable parameters, right? Basically, we parameterize the evolution equations. So the idea of that I'm trying to sell you with the energy-based approach is we start with a parametric energy and we parameterize the energy. And then we derive the evolution equation as a gradient flow. So obviously, it reduces the number of possibilities, right? Because the evolution equations can be more or less anything, right? But not every evolution equation is necessarily a gradient flow. So here already we restrict ourselves to maybe a very small subset of possible evolution equations, but what we get in exchange is we will be able to make some mathematical guarantees about the behavior of these equations. And here's an example. So here we have a heterophilic graph, right? So here the node colors represent the labels. So we have just red and blue. The positions here represent some two-dimensional feature space, right? So each node has two-dimensional coordinates, right? So think of them as the node features. And here the task is I want to separate between the reds and the blues, right? So to completely pull them apart. You can see that we can do it, right? So here there are these trajectories that separate the reds and the blues entirely. And we do it by considering this parameterized version of the directional energy, which physically can be interpreted as two contrasting forces. So we have attractive forces that work along the positive eigenvectors in the space of features, right? So these are positive eigenvectors of the matrix W. And we have repulsive forces that work along the negative eigenvectors of W. And then the evolution equation is just this constant convolution type processing of the graph, right? So why do I call it convolution? Because here the matrix that sends information across the nodes is fixed. It's independent on the features, right? So we call this the convolutional flavor, right? And here is the shared matrix W that works across the feature dimensions, right? So this is the channel mixing matrix. What we can show is that this very simple diffusion equation, right? So there is no nonlinearity here, it's all linear. If we appropriately design the channel mixing matrix, so it has to be symmetric for it to be a gradient flow, and it needs to have sufficiently large negative eigenvalues. So then we have these, the repulsive forces are sufficiently strong. We can probably avoid oversmoothing, right? So we'll not have this situation where everything collapses into a single point. We have a situation like here, where we have nice separation between two different classes of nodes. Okay, so there is this kind of folklore that you often read in graph neural network literature that convolutional type architectures do not work with heterophilic graphs. So this is not true. You can see here that they do actually work. Any questions? Okay, so this was homogeneous diffusion. So if we want to make an analogy to non-homogeneous diffusion, we need basically some sort of nonlinear diffusivity function. And the way to define it on a graph is basically by using this learnable diffusivity, right? So we can parameterize this function. And if I write this diffusion equation, what I get essentially is a GAT, right? So the graph attention network. So with appropriately normalized, I get that this is a version of a nonlinear diffusion equation, right? So the graph attention network is a version of this diffusion equation. We can also make more interesting diffusion equations, so we can combine two types of physical processes. We can combine what is called diffusion and advection. So maybe a good physical metaphor to think is when you have a river with different concentration of salt, right? So you have the chemical diffusion of salt, and you also have the flow of the water in the river, right? So these are two different phenomena, right? So the particles move in different ways. So one is called diffusion and another one is called advection, and we can design an architecture. One looks like a transformer, another one looks like a message passing architecture that combine basically that model both phenomena, and we can basically we can discretize it and learn in this way. Okay, but this was maybe a little bit of cheating because I promised you that a continuous model for the graph, right? And so far I only gave you a continuous model for the time, for the layers, right? But if we again look at how diffusion looks like on in the Euclidean case, right? So I can discretize the diffusion operator, right, or the Laplacian operator in different ways, right? So these are all legitimate discretization of the Laplacian, right, or any of their combinations because it's a linear operator. So basically what I'm trying to say here is that the computational graph, right, so the way that I discretize, that I construct the graph is really arbitrary, right? So it depends mostly on the numerical property of this discretization. So the analogy that we can make here is also comes from image processing, where instead of considering nonlinear diffusion, you can consider non-Euclidean diffusion. So if you think of an image, right, and you have a diffusion that works differently at every location in the image, think of standard linear diffusion, but now instead of an image, you have a manifold. So the image is embedded in the joint space where you have the feature coordinates, right, R, G, and B channels, and the positional coordinates, the X, Y positions of the pixel. And by virtue of this representation, by this embedding, we can define a metric on this manifold, and we can define appropriate version of the Laplacian on this manifold with respect to this metric. It's called the Laplace-Beltrami operator. And again, the diffusion equation that is defined here minimizes some generalization of the Dirichlet energy that is called the Polyakov energy. So it comes from string theory in physics. So bottom line, we can do the same thing in graphs. So we have now a joint space where we have the feature coordinates and the positional coordinates of the nodes, and we can evolve both at the same time. So we can consider the change of the positional coordinates as some soft version of graph rewiring, so we can introduce or cut edges, and the evolution of the feature coordinates as the standard information diffusion on the graph. So it looks a little bit like this. So we have the different colors here represent different features. The positions of the nodes represent positional coordinates, and the connectivity also changes, right? So we are rewiring the graph as we evolve it, right? So that's this Beltrami flow on a graph. So I believe that I will probably stop here. I think we are at time. I have more stuff to talk about. I can talk about Ricci flows and curvature, but probably I will not have 10 minutes are not sufficient. So maybe if you have any questions, please ask now. Yeah.
Sir, why in GCN are we not assured that over-smoothing will be avoided?
So GCNs, right? So basically what we need to make sure is that, so let me go back maybe to the expression. So I think it's an important clarification. Let me see where was the slide here. So indeed in a GCN, right, so you have some normalized adjacency matrix, your features, and then this matrix W. Now in GCN, this matrix W is arbitrary. So here we must make some assumptions about W to make sure that it's a gradient flow. So it must be symmetric, right? So in GCN, it's not symmetric. And it must have sufficiently large negative eigenvalues, right? So why this folklore tells that GCNs do not work for heterophilic graphs? Because the typical motivation is this A, right? So the adjacency matrix acts as a low-pass filter. So I'm averaging my neighbors, right? So if the neighbors are similar, right? So if they're all apples, then averaging apples makes sense, right? But if you have apples and oranges, averaging apples and oranges makes no sense, right? But the reality is more subtle. So I have two filters that act on this X, right? So if I were to column stack X, basically it will be a Kronecker product of A and W. So they have their own eigenvalues. I can do actually a Fourier transform of A, right? So that would be the standard eigendecomposition of the graph of Laplacian, right, or the graph adjacency. But also W is a symmetric matrix. It also has orthogonal eigendecomposition. So it's the product of their eigenvalues what matters. So if matrix W has sufficiently large negative eigenvalues, it allows to undo this blurring effect, the averaging effect of the adjacency matrix. So that's why they act together. So
I follow why this happens, but why simply adding some regularization or by normal loss, why is this not assured? Like, why does this not happen in GCNs then?
So it's not, well, you can learn it in principle, yes, but it's not guaranteed. Right? So because in GCN you can have an arbitrary matrix. Here I force you to design it by design, by construction, the matrix is such that this will happen. So we actually parameterize the matrix W with separating it into negative and positive part. And we make sure that the negative part is sufficiently large. So basically it's a disciplined way of choosing your parameters and choosing your, for example, the parameters are shared across layers in this case, right? So we don't have any nonlinearity, so we show that all this is not needed. So we only do once a nonlinear encoder and maybe a nonlinear decoder, but all the diffusion part is linear.
Great, Professor. Can you please clarify the moment with non-homogeneous diffusion and what the main physics difference with this case?
So the non-homogeneous diffusion for images or for graphs?
For graphs.
For graphs. Okay, so the main difference is here, that we have this nonlinear function, right? So this is what we call the attention. So it's a special type of symmetric attention in this case. But instead of having something constant that depends only on the structure of the graph, we have a function that depends on the features, right? So in the standard diffusion, I will have here something like Wij, right? Here it's A that it depends on Xi and Xj.
Okay, thank you.
Any more questions? Good. I guess then you have lunch. Thank you.